Okay, hello and welcome to a worked example of Fourier series. So what you see on the screen is actually the definition of Fourier series from your textbook, which is the ZIL definition, 12.2.1. And I recommend that you write it on a piece of paper or a sticky note and just stick it on every piece of paper you're working on because it's nice to have this as a reference. So what we're going to do is work through this example. F of x is equal to this piecewise function that equals -1 when x is between negative pi and 0, non-inclusive. F of x equals 1 when x is between 0 and pi, not inclusive. And f of x is equal to 0 when x is equal to negative pi, 0, or pi. So I'm just really quickly going to draw what this looks like. This is, as spoiler alert, it's a square wave. So when x is between negative pi and 0, the value is -1. So we have, so negative pi and 0, the function's equal to -1. And notice the open circles, which indicates that that function is not actually equal to 1 at those values, or -1, sorry. Okay, and then between 0 and pi, when x is between 0 and pi, the value of the function is 1, so we do the same thing up here at 1. And then when x is equal to negative pi, 0, or pi, that's where we can actually draw our dots, and the function's equal to 0. Okay. So you can see that it starts to form a bit of a square wave. Now, this function's equal to these values, but the idea here is that f of x is periodic. And so this pattern repeats itself every certain interval, and we need to figure out what the interval actually is. So what I'm going to do is walk you through about 5 steps of how to find the Fourier series. And really what we're trying to do is we're actually trying to find this function here, f of x, and represent it in a Fourier series. Okay, so finding a Fourier series is our goal of f of x. So step 1 is actually going to be to define our interval. And what we're really interested in is we're interested in figuring out what the value of p is. So this p that shows up in the formula everywhere is effectively half the interval. So or the the length. So our interval in this particular case is negative pi to pi, and this means that the total period, right, this is 2 pi. So from negative pi to pi is 2 pi, so this is 2 pi periodic. And that means that p is defined, which is half of the period, is defined to be pi. So this is actually a really important step. If you don't actually have this down, then the rest of it's very hard. So that's why it's step 1, is to actually define p. Okay. So step 2 is to find a sub 0 or a naught. And you can do this in any order. I just like to do the easiest one first. So a naught. And the reason why I'm making this video is because I just want you to see and hear where all of the pieces fit. Okay, so what I'm going to do is I'm actually going to I'm going to write out the equation without changing anything so you can see what changes. Okay, so I'm just going to copy this down here. So a naught, this is the definition. Okay, so without changing anything, I've literally just written down the definition. Okay, so now we know that p is equal to pi. And because this function is piecewise, what we want to do, I erased the negative p. What we need to do is we actually need to break up this integral from negative p to p into 2 integrals. So that way we can add them up, and that's how integrals actually work. So we're going to break up into 2 integrals. Okay, so that I'm just going to start replacing the unknown values that with values that we know. So p is equal to pi. So now I have 1 over pi. And I'm breaking up this integral into 2. So I have the integral from negative pi to 0 of negative 1. Now negative 1 is our f of x. So f of x is equal to negative 1 when x is between negative pi and 0. So I'm actually, it hurts me to actually write negative 1 here. I'd rather just put a negative out front, but I want you to see where everything actually goes. Okay. So, and then our next integral goes from 0 to pi, and this hurts even more. F of x is equal to 1 on this interval, dx. Okay. And now we just integrate. Okay. Actually, what I did was I actually simplified, so we can simplify actually, just so you can see what happens. So I'm sure you're following, but negative pi, 1 over pi, and we have negative, the integral from negative pi to 0 dx plus the integral from 0 to pi of dx. Okay, so now we're just going to integrate. Okay, so the integral here, 1 over pi, what we have is we have negative x evaluated from negative pi to 0 plus x evaluated from 0 to pi. Okay, so be very, very careful when you do this because the signs are actually very important. So what we have here is we have 0 minus, that's part of the formula, right? We evaluate from the b first and then a. So b is 0 and minus, but x is already negative. So I have a negative and then I'm plugging in a negative pi. So I'm just going to show you where all the negatives go. And you can see I have an odd number of negatives, so therefore it's going to be negative pi. Plus, and then we have pi minus 0 here. Okay, so you should see here that you get 1 over pi, negative pi plus pi, which of course we know to be 0. Now, this actually should make a lot of sense. And that's because you actually have seen this formula before. The formula for a naught, 1 over p times the integral of negative p to p f of x dx. Hopefully you recognize this as the formula for an average. This is literally the average of f of x. And if I actually go up to the graph, well, what is midway between negative pi and pi? Well, it's 0. Or sorry, between negative 1 and 1. Sorry, what we're doing is we're looking at the value of f of x. Well, what is the average of between 1 and negative 1? Well, it's 0. So the average of the function is in between our f of x. So that actually should make sense. So we should get 0, and we do. Okay. So that's a sub 0, or a naught. The next one we're going to tackle is a sub n, and just I like to copy the equation over just so I always have access to it when I switch pages. So all right, so here's our equation. So I'll wrap this in purple so we don't think it's part of the problem. Okay, so it's just always nice for me to have that as a reference. Okay, so now step 3 is to find a sub n. Okay, so again, I'm just going to copy the exact formula over so I have this to reference. And that way you'll see when things are actually changed. All right, so here's a sub n. Here's our definition. Okay, so a sub n, we know again that p is equal to pi. And again, this is piecewise, or f of x is a piecewise function. So therefore, we're just going to break up the integral into 2 integrals. Okay, so what we have here is 1 over pi. And again, I'm going to just be very careful to put every single piece of information down so you can see what happens to it. So our first integral from negative pi to pi, again, f of x is equal to -1. But now we have to contend with this cosine term. And notice what happens with the argument of cosine. So we have cosine of n pi over p times x. Well, p is equal to pi. So n pi over pi x. And you can see what was going to end up happening here are the pi's are going to cancel. And you'll end up with cosine of nx. So, but I'll keep going here. Dx plus integral from 0 to pi of 1 this time, cosine of n pi over pi x dx. Okay. So again, the pi's cancel, so that actually significantly simplifies the argument of our cosine functions. And I'll simplify this, 1 over pi. The integral from negative pi to 0 of cosine of nx dx plus the integral from 0 to pi of cosine of nx dx. Okay, so I must warn you here not to commit mathematical treason and think that you should add these up. And actually, I missed a negative sign. So, so there should be a negative here from that -1. So do not resist the urge to add these up. It is bad because these integrals are evaluated at different values. So because you have different limits of integration, you cannot add these up. And if you try, you'll get wrong answers. So don't do that. Okay. So 1 over pi. And what we're going to do now is just simply integrate. So the integral of cosine is sine. So I have negative sine of nx, and then I divide through by the argument, or the derivative of the argument, right, which is 1 over n. Chain rule, evaluate from negative pi to 0, plus 1 over n sine of nx, evaluated from 0 to pi. Okay, so if you recall from lesson 30, or from even before, from any of your calculus courses, or trig really, from lesson 30, that sine of any multiple of pi is equal to 0. So you can see that if I plug in 0 here and I plug in pi, both of these sine terms go to 0. So we can actually cancel these. Both of these terms are 0 at both endpoints, and therefore we end up with 0. And again, this actually should make quite a bit of sense logically. So if I go back to the plot that we made, the graph of the square wave, you can see that if I were to crudely draw a sine, any sort of trig function, right, what I would end up with is I would end up with something that looks a lot like a sine wave. And so it doesn't really make sense that we would have any cosine terms. And remember, a sub n is giving us the values of what our cosine terms are. If you look actually at the f of x definition here for Fourier series, a sub n determines the amplitude or the weight of our cosine terms. And it really doesn't make sense based on the shape of this function that we would have any cosine terms at all. So the fact that we have a sub n always equals 0 is not surprising. So I encourage you to sort of think critically about what you're actually getting. Okay, finally, step 4 is to find b sub n. And again, I will go and copy the equation here. Or the formula for b sub n. And erase my random arrow. Okay, so b sub n, again, p is equal to pi, and the function is piecewise. So all we need to do is break up the integral into two integrals. So 1 over pi, integral from integral from 0. Sorry, I'm going to move this down a little bit. You don't need to erase. You probably did it correctly. 1 over pi, the integral from negative pi to 0. And again, I have negative 1, that's f of x on this. When x is between negative pi and 0, f of x is negative 1. Sine of n pi over pi x dx. So the only difference here between a sub n and b sub n is that we have sines instead of cosines. So plus 0 to pi 1, which is our f of x, sine of n pi over pi x dx. Okay, so let's simplify this. 1 over pi, the integral from negative pi to 0 of sine of nx dx, plus the integral from 0 to pi of sine, I missed my negative again, sine of nx dx. Okay, so be careful with these negative signs because you can see they're actually quite important. Okay, so now we integrate. Again, do not commit heresy here and start adding the negative sign and the sign. It will not work for you, so don't do that. Do not add here. The limits of integration are different. You cannot add them. Okay, so if we integrate, remember that the integral of sine is negative cosine. So what we end up with here is 1 over n, keeping in mind the chain rule, cosine of nx. It will have evaluated from negative pi to 0. Plus, and then we have a negative here because the integral of sine is negative cosine. Negative 1 over n cosine of nx evaluated from 0 to pi. Okay, now what you notice here, is you probably have already figured out that this is not just going to give us 0. So what I'm going to do is I'm going to pull out a 1 over n just to make this a little bit cleaner. So 1 over n pi. And now we just need to evaluate. So now we're not going to get a whole bunch of zeros. So we pulled out the 1 over n. So I have cosine of n times 0. So cosine of 0 is 1. And then minus cosine of n, actually I'm going to write this out, cosine of n, and it's really negative n pi. And I'm just going to leave this in the unevaluated form for now, minus, okay, so I'm following my formula, and then I have cosine of n pi, and let me put parentheses around here because I need to subtract, minus cosine of 0. Okay, so I have this cosine of 1 over here, and so I will just go ahead and replace this guy right here, cosine of 0 with 1, because we know that's 1. Okay, so let's be very careful with the signs and very careful with what we come up with here. So 1 over n pi. All right, so I have 1 and minus cosine of n pi, which is, I'm actually going to leave it like this. Actually, what you can see here, and I can do this in one step, I think. What you can see here is I have a 1 in this line above, and then I have a minus. I'll use a different color so you can see what I'm actually pointing at. You have minus a negative 1. So you can see that we're going to actually end up with 2 here. So I will have a 2. And notice I have a negative cosine of, well, I didn't actually mention this. Some of you may have already figured this out, actually, that cosine of negative n pi is actually cosine of n pi because cosine is an even function. So we have 2 cosine of n pi terms here, and they're both negative. So in this line below, I have 2 minus 2 cosine of n pi. Okay, so that's what we've got. And so what we need to do is figure out what this actually equals. So it turns out that much like the orthogonality discussion in lesson 30, the answer actually depends on if n is odd or even. So b sub n is equal to 2 values. Turns out that if n is even, if we just look at it this way, if n is even, let's say n is 2. So for n is 2, what I would get inside the brackets, I don't really care about the outside, what I would get inside the brackets is I would get 2 minus 2, cosine of 2 pi is 1. And you can see that I'm going to get 0. And that happens with every single even value of n. So for n is even, b sub n is actually equal to 0. Okay, so now for n is odd, what would happen, let's try n equal to 3. Well, for n is odd, so I have 2 minus 2 times cosine of 3 pi. And notice that's going to give us, that's going to give us a negative value. So what you're going to end up with is, you're going to end up with 2 minus negative 2, which is 4, right? So you end up with, and now I care about what's on the outside. So now I end up with 1 over 3 pi, right? And I have a 4 on the top. So notice that it's going to be 4 over whatever n is times pi. So my b sub n for odd n is 4 over n pi. And if you don't believe me, you can try a few values just so you can see the actual pattern, but this is what b sub n is equal to. Okay, the last step. The last step, so step 5, is actually to write out the Fourier series. And so I'm going to go all the way back to my original Fourier series without changing anything. So we can just start writing out all the different terms. All right. So the good news is that when you get here, we can actually start crossing a lot of things out. So what do we know? So we know that p is equal to pi. We know a sub 0, or a naught, is equal to 0. A sub n is equal to 0 also. And b sub n is equal to 2 values, just seems inconvenient. 0 for even n, and 4 over n pi for odd n. So let's start crossing some things out in a satisfying red color. So a sub 0 is equal to 0, a sub n is equal to 0. And remember that p is equal to pi. So if we write this out again, f of x, well, we get rid of a lot of this stuff. N equals 1 to infinity of b sub n sine of n pi x. Okay, so that is really what we have, where b sub n is equal to b sub n is equal to 0 if n is even, and b sub n is equal to 4 over n pi if n is odd. Now, one thing that you could do is you could just restrict in the summation that n is odd. This is not probably the best idea, just because if you have sines and cosines, you can't do that. So what I recommend you do is figure out a way, so instead of restricting n, cook the books such that any n you put in will give you an odd value, and that's what we're going to do. So I can instead say that b sub n is equal to 4 over pi times 1 over 2n minus 1. And that would be for n is greater than or equal to 1. And you can try this. If you plug in n is equal to 2, the denominator, this 2n minus 1 quantity, so you're plugging in n is equal to 2, you get 3. So it actually automatically makes it so that no matter what n you put in, you get an odd value. And that is the method I recommend. Okay, so if we were actually to plug that in, n is equal to 1, it goes to infinity of, now what I can do is anything without an n I can pull out of the summation, which is what I'm going to end up doing. So 4 over pi, and b sub n, the only leftover part is this part with an n, 2n minus 1. And now I can actually plug in that, that value that used to be n, sine of 2n minus 1 times x. Okay, this is your Fourier series right here. Okay, that's it for this walkthrough. I would encourage you to watch this again at half speed, just to make sure that you understand what's going on. I'm not saying that right now, but it is going to be very important that you understand how to do this.